Hey there, my name is Gokul, and today I'm going to talk about our work on imitation learning in the presence of unobserved confounders. Consider the problem of trying to learn to fly a quadcopter by imitating an expert pilot. Let's assume there's heavy gusts of wind that cause the quadcopter to deviate from the intended straight path of the expert. Now, what will happen if we try to apply a standard imitation learning algorithm like behavioral cloning to this set of demonstrations? Well, the learner is likely to pick up on the correlation that being a little on the left is usually followed by going even more to the left. If they ignore the fact that it was the wind that was the root cause of this correlation, they might attempt to reproduce the swerving behavior of the expert, causing them to deviate even further at test time due to the continued influence of the wind. More abstractly, the effect of a confounder like the wind in our previous example is to introduce temporal correlations in the recorded actions that do not have their true cause in the recorded state. We can visualize this effect graphically. At each time step, the expert takes an action responding to the observed state, and the MDP transitions to the next state. The persistent confounder U affects multiple actions. This means that when we try to regress from states to actions, standard approaches will produce inconsistent estimates of the expert's policy. This is because the confounding travels through the dynamics to influence the next state, leading to spurious correlations between recorded states and actions. The learner might then latch onto these spurious correlations to explain away the effect of the confounder by misattributing it to some element of the state, leading to poor test time performance. This is what leads to the increased swerving in our quadcopter example. What we'd like to learn instead is a policy that flies as close to straight as the expert does. It turns out we can find such a policy by applying a technique from econometrics called instrumental variable regression. Consider trying to regress from x to y, both of which are influenced by a confounder u. Ideally, to mitigate the effect of the confounder, we would randomize over x via a controlled experiment. However, if we only have observational data, we can achieve a similar effect via a source of randomness independent of the confounder. This variable is called an instrument, which we denote as z. The key idea is that we can condition on z to counter the effect of the confounder. In our model, the past state acts as an instrument as it is independent of future confounding. We can leverage this past state instrument in two ways. The first is via simulator to resimulate the transition from the past state to the current states, leading to fresh draws that no longer share a noise term with the observed action in the recorded dataset. We can then apply standard imitation learning to this new dataset, a procedure we call double. We show in our paper how this is equivalent to solving a particular two-player zero-sum game between a policy player and an adversary that can upweight residuals based on the value of the past state instrument. We term it residual. Notably, this game-theoretic procedure can be performed completely offline. We prove a performance bound for both algorithms in the exogenous setting, where epsilon and delta are measures of training error, kappa of pi a measure of the weakness of the past state as an instrument, and t the horizon of the problem. Notably, behavioral cloning does not have a similar bound in the setting, so even if one was able to drive training error all the way to zero, they have no guarantee of recovering a policy of equivalent quality to that of the expert. Empirically, we find that both of our algorithms are able to significantly outperform behavioral cloning and matching the intended action of the expert on a simulated lunar lander task with exogenous noise. We can also compare the output of one of our causally consistent approaches to behavioral cloning to find the areas of the state space where the effect of the confounder is particularly strong. For the lunar lander task, the red dots indicate these areas. We also briefly consider an extension to our previous graphical model where a confounder can affect more than two time steps. For example, the wind in our drone example might affect quite a few time steps before dissipating. This sort of persistent confounder needs one has to reach back even further in time to find a valid instrument. States further back end up being weaker instruments as they are less correlated with the present. We plot the weakness of the instrument, kappa, for a linear quadratic Gaussian problem, and we see it grow exponentially with the persistence of the confounder. Thank you for your time, and please check out our full paper and videos at a link on the screen.